Okay, there we are. Good morning, lads and ladies, and welcome back to MAP2302 Differential Equations. Today's going to be a fun day because today's the day that I finally get to teach you the most important method for solving differential equations. Those of you going into engineering or physics, chemistry, especially analytic chemistry, or any of those places where differential equations actually show up, you'll be startled to see how often the method we use today is the one to use. Exception to this is the Laplace transform. The Laplace transform, which we're going to talk about at the end of the semester, may be slightly more prolific. Of course, I'm talking about separation of variables. So today we're going to learn how to solve differential equations through separation of variables. Looks like my black pen has wandered off. Let's see if I have a blue black pen here. We'll take a gamble with purple, maybe. Yeah. Okay. All right. Let's get to it. I also have a kind of funny story to share with you guys today, too. A sort of cute, interesting differential equation that was given to me by an evil physicist back when I was an undergrad, just to mess with my head. So this is MAP2302. It's differential equations. Today is a lecture. Ooh, this pen is not good. And it's the 30th. All right, I'll ask you to bear with me while I go around and find a better pen. Baby, do you know where that big tub of black G2s went? That's where I left it. Oh, there it is. It's just way back here. Okay. Hopefully one of these is good. So today, we're going to focus pretty much just on separation of variables. And this is section 2.2. So those of you who are paying attention, notice we're going out of order, but there's a really good reason for that. There's some material from 2.1 that I'm really excited to share with you next week, but I want you to just solve some differential equations, right? That's the best way to get kind of your feet wet in this world, is to get to a place where you can actually look at some problems and solve them. So that's what we're going to do. First, a story. Story time. So back around 2010, I was finishing up my undergraduate in math at the University of Florida. That's where I did my undergrad. And a fellow who was at the time working on his PhD in operator theory, a specific type of analysis, mathematical analysis, he'd later go on to be an industrial systems engineer, because those sort of that sort of mathematics is especially useful to those guys working on optimization problems. His name was Joel, and Joel, knowing that when a problem gets into my head, kind of can't let it go, asked me to solve the ODE. I'm going to write it like this: f primed of x equals f inverse of x. So here, of course, f prime, this is like dy dx, right? And over here, f inverse, we mean inverse in the sense that like the natural log is the inverse of e to the x, or in the sense that the square root of x is the inverse of x squared, right? The functional inverse. So we're looking for a function whose derivative is equal to its inverse. And that's a strange thing, right? This is a very strange. Very odd differential equation. Because there's no nice algebra formula. or calculus formula for that matter. For F inverse. Right, you guys remember how to find inverse functions. You learned that back in your pre-calculus class, I imagine, where you like swap x and y and then solve for y, and sometimes you have to restrict the domain, all of that. There's a procedure for finding the inverse function, but there's no nice formula for it. And the way that that procedure shakes out depends very much on the type of function that you're working with. And since here we don't know a priori, we don't know ahead of time what kind of function f is, we can't even begin to hypothesize about the shape of F inverse. So I did something I'm going to show you guys how to do later in the term. I assumed F was analytic, meaning it has a power series expansion, and I started trying to express the left-hand side and right-hand side in terms of power series and solve the recursion for the coefficients. Didn't work out. I was able to get the first few terms of the power series through some nasty brute force methods. But I certainly didn't get the full solution. And I worked on it for about a week. And then this fellow, Joel, he came back to me and asked, so did you solve that problem I gave you? Did you find a function that solves this ODE? And I said no. And just to taunt me some more, he said, well, I gave it to my little brother. His little brother was 5 years younger than me or something. Gave it to my little brother, and he solved it in about 10 minutes. And I was furious. And about a week later, I had a few more terms of my power series, but I realized I wasn't getting anywhere. So I talked to Joel again, and he shared something with me that was relevant to a homework question that you guys asked yesterday. I'm trying to remember who it was that asked the question. I think it was Malin. Asked that question about, what was it, question 10, where you have to find the values of m such that x to the m solves this equation. The trick to solving this differential equation right here is to assume that a solution of a certain form exists. So I'll go ahead and share this with you. If you want to try yourself, but I'll tell you to assume that f of x is a power function. So like a times x to the p. Kind of similar, very similar to the assumption that was baked into that problem, right? That f of x or y was x to the m. So here, if you assume that your function f is some constant times x raised to another constant, then you'll be able to go through and compute both sides here. You can compute the inverse of the power function reasonably easily. You can compute the derivative very easily. You can build the ODE and find the constants a and p. And you'll find, if you're familiar with any of that sort of magical geometry, golden ratio stuff, you'll find that the golden ratio plays a big role in this, which is surprising on so many levels. So it's a fun story. Similar in its nature to the homework question that was asked yesterday, but we didn't have time to talk about it. I just want to share it with you. All right, story time over. Oh, the moral of the story there. Moral of the story. Joel's younger brother is a physicist. Physicists are smart like that. That's why I married one. Physicists know when to make a simplifying assumption. Right? He didn't bother with power series. He didn't bother assuming that the solution was somehow more general. He just tried a few different things. He tried assuming it was exponential, and then the second thing he tried was assuming it was a power function. It came out right away. So making the right kind of simplifying assumption can be a big help. And if you strive for generality all the time, you strive to be perfect or fully mathematically rigorous all the time, sometimes it can bite you in the ass. So if you're like that, marry a physicist. Okay. Separable equations. So today we are talking about separable differential equations. What separable means is that you can split up the differential equation into like all y stuff on one side and all x stuff on the other side. And then you can integrate on both sides with respect to the respective variables. And that'll get rid of your derivatives in the differential equation. So this only applies to first order equations. Show you a very simple example first, I guess. So the simplest type of separable equation looks like dy dx equals just some function of x. Right? No other y stuff. You just have y prime and x. These can be solved. Period. Sorry. Period. These can be solved by integrating. Right? You know, if you integrate on both sides here, then you get I want this. So I'm going to show you the notation already. Yeah, so by integrating, yielding, integrating on both sides with respect to x. By the fundamental theorem of calculus, integrating the equation above yields y equals the integral of g of x dx. And we would have like a plus c here, right? I.e., like this, y equals, this is y equals capital G of x plus c, where capital G is an antiderivative. For little g. Not all separable equations are this simple. I'll give you a second to write and catch up here. In fact, while you do that, I'll refresh my coffee. Okay. All right, so if you just have like y prime or dy dx equals some function of x, you can integrate on both sides. If you have an initial value problem, like a differential equation like this, together with some initial conditions, you can plug those initial conditions in here to find the constant c. But if you're just trying to find the most general solution of the ODE, it would look like this. So solving this ODE is exactly as hard as integrating the function g. You know from Calc 2 that integration can be tricky. It's not always easy. So I'm not saying that these are always easy. I'm just saying that from a differential equations perspective, there's not an extra challenge here. In fact, this is the type of differential equation that you learn to solve in Calc 1. When you see those IVPs in Calc 1, like we talked about yesterday, they were always of this form. Right? They give you the derivative of a function and ask you to recover the function itself. I suppose it wouldn't hurt to do an example like this. But maybe first I'll show you more general separable equation. So in general, By the way, the word general in mathematics means like always works, right? Or the most broad definition. In general, separable ODE is a first order equation, first order linear, or no, not necessarily linear, I'm sorry, just a first order equation which can be expressed, which can be written in the form. I'm going to use the same notation your textbook uses here. Dy dx, or y prime, dy dx equals some function of x times some function of y. So remember, your general first order equation is dy dx equals f of xy. And that f of xy, that right-hand side, sometimes you can split that up into a pure function of x times a pure function of y. Not always, but sometimes. And if you can, then that equation is called a separable equation. The way we solve these by separating the variables. Separating the x stuff from the y stuff and integrating on both sides. I.e., or that is, I'm going to multiply both sides by dx. So I'll write the whole process out here. Dy dx is equal to g of x times h of y. Multiplying both sides by dx is a somewhat illegal thing because dx isn't a number. But if you take non-standard analysis or learn about hyperreal numbers, it's actually okay. So if I multiply both sides by dx, I'll get dy equals g of x times h of y times dx. And then I divide both sides by h of y. And that'll give me dy over h of y equals g of x dx. And now the left-hand side has all the y stuff. The right-hand side has all the x stuff. So I can solve the ODE by integrating on both sides. So hence, integral of 1 over h of y dy, that's dy over h of y, I'm just going to write it like that, equals integral of g of x dx. These are indefinite integrals, so each one would give you a plus c. You might call it like plus c1 on the left and plus c2 on the right. But then you can move the c1 over to the other side, so we just write 1 plus c at the usually on the right-hand side. And now you've got it, right? You'll have some expression involving y over here. You'll have some expression involving x over here, and then a plus c. And then you try to solve that expression for y, right? You try to solve the resulting equation for y. So let's say then, if possible, solve for y. You remember from Calc 1 the difference between an implicit and explicit expression. if you're unable to solve for y, right, you have some expression on the left-hand side here where you can't solve the equation for y, then you would say what you're looking at is an implicit solution to the original ODE. If you're able to solve, then you'd call that an explicit solution. Okay. Any questions about the kind of setup here? Suppose I need a period here. All right, then let's look at some examples. The zero things, zero. Let's do one of those super easy examples we talked about. Just to remind you, one of those things that's looks like it's coming from Calc 1. So let's solve the ODE dy dx is equal to 1 plus e to the 2x. This is a separable equation. The function on the right-hand side here doesn't have any y's, only has x's, no y's at all. So to separate variables, I would say, okay, dy is equal to parentheses 1 plus e to the 2x times dx. So even though this is one of those super easy types that you saw in Calc 1, I'm going to use the kind of notation and methods of separation of variables to introduce you. This is actually an if and only if. So now we can integrate on both sides. What is the integral of dy on the left-hand side here? What is this? Someone help me out. Good, just y. Or you could say y plus c, but like we said earlier, we're going to group all the plus c's together on the right-hand side. So yeah, the integral on the left, I would just write that as y. Okay, and somebody else, what's the integral of 1 plus e to the 2x? Who can help me with that?
X plus 1/2 e to the 2x.
Very good, very good. The integral of 1 is x, and the integral of e to the 2x is 1/2 e to the 2x. And then I would write a plus c here. If you forget, I'm only going to show you this once. Integral e to the 2x dx. You do this via a little substitution. I would say z equals 2x, which means dz is 2dx. And that means dx is 1/2 dz. So this would be integral e to the z times 1/2 dz, which is 1/2 e to the z plus c. And then that would be 1/2 e to the 2x plus c. All right, that's the only time I'm going to remind you how to do u sub. So here you have your solution. You're done. All right, this is it. And this is as easy as differential equations get. It is a separable equation where there aren't even any y terms, just y primes and x's. Questions on this one? Okay, we just solved our first differential equation. Let's try one that isn't quite as simple. How's about Yeah, we can go for, well, let me grab an easy one first. We can go for something like, that looks good. Yeah. Equals 4y. This is not in that sort of standard form, right? I've got an x over here. So the first thing I would do is put this in that standard form. However, the differential equation is given to you, the first thing you should do is try to write it as like dy dx equals some shit on the right-hand side. So here I'll rewrite this as dy dx equals 4y over x. I'll divide both sides by x. Okay, is this equation separable?
Yes.
Yeah, how would I separate the variables?
Divide the y over
Good,
and then multiply the dx.
very good. So if I divide both sides by y and multiply both sides by dx, I'll get 1 over y dy equals 4 over x dx. I've just separated the variables. And my next step would be to integrate on both sides. So I have integral 1 over y dy equals 4 times the integral of 1 over x dx, popping out the 4. Right, that 4 is a constant multiple, he can come out. These integrals are not hard either, right? What's the integral of 1 over y dy?
Natural log of y.
Yeah, and I should be maybe a little bit careful. I should maybe write it as like ln of the absolute value of y. I don't have any reason to suspect that I'm dealing with negative values here, so I'll leave it as just ln y. But if we were being ultra careful, absolute value is not a bad idea there. And over here, the integral of 1 over x dx is also the natural log of x. So I'll just write it as ln x, assuming everything here is positive. Make a note of this. Assuming that both x and y are greater than 0. Okay. Unlike the last problem, I don't have y equals some stuff. I have the natural log of y equals some stuff. So this is what's called an implicit expression, an implicit solution. How can I get an explicit solution?
Multiply both sides by e.
I think you're thinking the right thing, but it's not multiplication that we need to do. How do
you raise both sides to the e?
That's getting closer, but it's still not quite right. I don't want to raise both sides to the eth power. I want to
Would it be e to the both sides power?
Mhm. There's a word for that operation. It's called exponentiation. So we'll exponentiate both sides base e. So I'll get on the left e to the ln y, and I trust that everybody would have done this. I'm just trying to teach you the vocabulary. On the left-hand side, I'll get e to the ln of y. And on the right-hand side, I'll have e raised to the ln of e raised to the 4 ln x plus c. These guys don't get separate e's, right? We're just sticking both sides in the power of e. So it's 1 e on each side with everything. Okay, e to the ln of y, that's y. Can I clean up the right-hand side? Any
Well,
advice?
C is just a arbitrary constant, so you can move that out.
There's a sense in which I can move it out, but I want to be very clear about it. Algebraically, how can I simplify this expression?
You can separate it to e to the c times e to the 4 ln of x.
Very good. Right, this is one of those basic rules for exponents, that if you have something raised to a sum of two powers, that is the product of that base raised to those two powers. So the algebra rule here is that a raised to the b plus c is the same as a to the b times a to the c. Okay, we're almost there. I can clean up e to the 4 ln of x pretty substantially. And I can also relabel e to the c as a new constant. So I can call this y equals, I'm going to do two things here. I'm going to use a rule for logarithms to bring this 4 inside the log. So I'll have e raised to the ln of x to the 4. That's a kosher algebra rule. One of the rules for logarithms says that a number out front of logarithm can be brought inside as a power. And then this e to the c, I'll call this just like k. Just to make life nicer. If c is an arbitrary constant, then e to the c is an arbitrary positive constant. And so finally, we get y equals e raised to the natural log of x to the 4 is just x to the 4. So I have k times x to the 4, where k is a positive arbitrary constant. So that original differential equation is solved by any constant times x to the 4. Right, this is the function that would solve that differential equation, as long as you're using a positive constant k. Questions on any of these steps? Feeling good? Okay. I want to do one or two more examples here. We might wrap up a little bit early with the material for this week, which would, fine, nice. If that's the case, then I'll show you something neat that I found online for next week's material, just to kind of get you ready, get you primed. But before we do anything like that, I want to do at least one more example here, maybe two more examples of separable equations, because they're just so important. This next one is going to be the first one we've done that involves any more kind of complicated integration, trigonometry, stuff like that. So here's our next example. I want to solve the initial value problem e to the 2y minus y times the cosine of x times dy dx is equal to e to the y times the sine of 2x. Subject to the restrictions or the initial conditions, that y of 0 is equal to 0. So the solution curve should go through the origin. Yeah, okay. So if I take my ODE, which is looking a little bit complicated, a little bit intimidating, and I divide both sides by the cosine of x, I'll write out every step here. E to the 2y minus y times cos x dy dx equals e to the y times the sine of 2x. I'll get, dividing both sides by cos x, e to the 2y minus y times dy dx equals e to the y sine of 2x or cos x. And at a glance, that right-hand side might look a little bit intimidating, but there's something we can do to make it much nicer. I guess let's go ahead and finish our separation of variables. Let's separate the variables and then we'll worry about it. But I want you thinking about what I can do to clean up sine 2x over cos x. So next I'll divide both sides by e to the y. 1 over e to the y times e to the 2y minus y. And multiply both sides by dx. So I'll have just here dy, and over here I'll have sine of 2x over cos of x dx. Those who took Calc 2 with me should be aware of the simplifying trick for the right-hand side. How do I clean this up?
You can change that to 2 sine x cosine x.
Excellent. I can use the double angle identity for sine. Sine of 2x is 2 times the sine of x times the cos of x. And that will allow me to cancel the cosine term. On the left-hand side, I'm going to do something also. Because I know I have to integrate this and I have to integrate this. And those are both really, looking a little intimidating, at least at the moment. After we clean this up using this identity, this will be easy. But over here, what can I do here? What if I write this as e to the negative y times e to the 2y minus y dy. And then over here, I'd have 2 sine x cos x over cos x dx. You can cancel the cosines. And over here, I'm going to distribute the e to the negative y. E to the negative y times e to the 2y is just e to the y. You add the powers, right? And then we'll have minus y e to the negative y. Not much can be done there. Dy, that's my left-hand side. And on the right-hand side, I just have 2 sine of x dx. All right, that's all the algebra done. From here, we're going to integrate. So I'm going to pause for a second, make sure your notes are clean, and see if you have any questions about what we've done or why we've done it.
So next you would multiply both sides by arc sine.
Nope, next I would just integrate on both sides. All right, so I've separated my variables. And before I can try to solve for anything, I need to integrate to get rid of the derivative stuff. I've got all y stuff times dy on the left, all x stuff times x on the right, or times dx on the right. So we're going to go ahead and integrate, and then we'll try to solve the resulting equation. I don't have any problem integrating the sine of x. I'm pretty happy to have just sine of x dx over here, because that's an easy integral. On the left-hand side, I have a little bit more work to do regarding the integration. E to the y is easy to integrate. How do I integrate this piece?
Integration by parts.
Very good, very good. Okay, so we're going to have some integration by parts to do. So I'll say now we integrate on both sides. I'll have e to the y minus y e to the negative y dy equals 2 times the integral of sine x dx. And my right-hand side, I'm going to split this up. We'll call this right-hand side, left-hand side. RHS, right-hand side, to integral sine x dx is equal to what? What's the integral of sine?
Cosine? Or no, negative cosine.
Negative cosine.
Yeah, we got to remember how the signs work. So this is going to be -2 cos x plus c. And my left-hand side requires integration by parts. So let me continue this on the next page.
Your u would be y, correct? Because that just differentiates to a constant.
Yeah, I'm going to split the integral up. One of those pieces I'll just handle on its own. The other piece here, I'll use IBP. And within that IBP, I'll be picking u as y and dv as e to the negative y dy. So I have integral e to the y minus y e to the negative y dy, which is equal to integral e to the y dy minus integral y e to the negative y dy. And in this first piece, I'll just have e to the y. And again, I'm not going to write another plus c here. I've just got this one plus c from the right-hand side. I'm not going to write any plus c's from the left-hand side. The second integral, and I'm splitting it up because this does not require integration by parts. This does require integration by parts. So the split up here is necessary. We use IBP, integration by parts. And however you learn this, the way I teach it in my Calc 2 classes, most of the time you can follow the LIPET rule. So look for logarithms, look for inverse functions, then polynomials, then exponentials, then trig. And that helps you choose your u. So I don't have any logarithms in here. I don't have any inverse functions in here. I do have a polynomial function in here. Y on its own is a polynomial. So I'll pick u to be y and dv to be everything else. If you have another way you like to think of integration by parts, that's fine. Just make sure you know what you're doing. So here's my IBP setup. The differential du is dy, right? Because the derivative of y is 1. So du is equal to 1 dy. And if you integrate e to the negative y, integrate dv to get v, integral of e to the negative y is negative e to the negative y. Okay. So here's my little IBP table for that second integral. Maybe I'll continue this down here. So we'll have equals e to the y, that's from that first integral, minus, and then open up a big parentheses because this whole integral here is being subtracted. So everything that comes from our integration by parts needs to be subtracted. So open up a big paren. Your integration by parts formula, if you remember, is u times v minus the integral of v du. So u times v, that's negative y e to the negative y, right? Y times negative e to the negative y, minus the integral of v times du. So that's minus the integral of negative e to the negative y times dy. Okay, use parentheses carefully. We've got a lot of negatives that need to be managed here. That's e to the y minus this minus y e to the negative y. This negative will come out and make that plus integral e to the negative y dy. Don't get sloppy with your notation. Write your dy's, write your dx's. Integral of e to the negative y, I'm going to clean this up before I distribute this negative. Integral e to the negative y is negative e to the negative y. This is e to the y minus negative y e to the negative y minus e to the negative y. And again, not writing any plus c's here because we got that one from the right-hand side. Now I'll distribute the negative in front of the parentheses. We get e to the y plus y e to the negative y. Minus minus here makes plus, and minus minus here makes plus. So plus e to the negative y. That's my left-hand side. You could, between these two terms, you could factor in e to the negative y if you wanted to, but I would say you don't have to. My right-hand side, if you recall, my right-hand side is negative 2 cos x plus c. So left-hand side and right-hand side are equal to each other. My left-hand side is this. So I'll say, therefore, the ODE is equivalent to e to the y plus y e to the negative y plus e to the negative y equals negative 2 cos x plus c. And this is certainly an implicit solution, right? This is not an easy equation to solve for y. There's no simple way to isolate the y terms here without having it in terms of other y terms. I could solve for this y, but then these pieces would still be floating around on the right. So this is an implicit solution to the ODE. But what we were asked to solve wasn't just the ODE, we wanted to solve the initial value problem. So the IVP has initial conditions that y of 0 is equal to 0. Which is the same thing as saying that the solution curve should go through the origin. Or when you plug in 0 for x, y should be equal to 0. So I'm going to plug in 0 for x here and 0 for all of these y's, and that will let me solve for c. Hence, e to the 0 plus 0 times e to the negative 0 plus e to the negative 0 is equal to negative 2 times the cosine of 0 plus c. And this will let me solve for c. E to the 0 is 1. 0 times e to the negative 0 is 0 times 1. and e to the negative 0 is 1. So maybe notations here. This is 1. This is 0. This is 1. What is the cosine of 0?
1.
It's also 1, right? Which means this whole piece here is negative 2. So what I get is my left-hand side is 2, right? 1 plus 0 plus 1 is equal to negative 2 plus c. And that means that c has to be 4. All right, add 2 to both sides. 4 is equal to c. So the implicit solution to the initial value problem is e to the y plus y e to the negative y plus e to the negative y. These pens, I bought all these new G2s and they all suck. Equals negative 2 cos x plus 4. So this one quite long. I'd like you to take your time, look back over your notes, see if there are any gaps, any pieces that make you nervous, anything like that. I'm happy to go back and show you any part of this or talk about any part of this. Please take a second, make sure your notes are good. Yeah, that's a good one. Any questions on this? Okay, a few comments. All of the integration techniques you had to learn in Calc 2 are going to come back here. There are going to be some problems that require you to do partial fractions. There are going to be some problems that require you to do trig sub. There are going to be some problems that require the methods of 7.2 in your textbook, the calculus textbook of trigonometric integrals, right? Using identities and making substitutions. So you need to be a crack integrator to get through this stuff. And that's going to be true for the whole class. Let me go ahead and do one more example here of a separable differential equation, and then I'll let you guys go. The kind of bonus topic for today, if we have time, is direction fields, but that's a formal topic for next week, so I may just show you the applet real quick. All right, let's do a fun one. This is a classic problem. Example. Oh, it's a bad time. example, solve the initial value problem, dy dx is equal to negative x over y, subject to the initial conditions, y of 4 is equal to negative 3. Okay. The separation of variables here is not hard. Algebra is easy this time. So that original expression, dy dx is equal to negative x over y, is equivalent to saying, multiply both sides by dx, multiply both sides by y, equivalent to saying that y dy is equal to negative x dx. And now I can integrate on both sides. So the integral of y dy is equal to the negative integral x dx. Both of those are power rule integrals, nothing fancy. So that's 1/2 y squared is equal to negative 1/2 x squared plus a constant. I can add the x squared over. Let me be clear here. I've got some options. Depending on how you want to express this, explicitly or implicitly, we could, well, let me show you something here. So from here, we can get the implicit solution one half y squared plus 1/2 x squared equals c, which is equivalent to multiply both sides by 2, y squared plus x squared equals 2c. Why would I maybe want this implicit expression rather than the explicit expression you get from taking square roots?
That's the formula for a circle.
Yeah, because I know exactly what that is. That's a circle centered at the origin of radius square root of 2c. Which is a circle of radius square root 2c centered at 0, 0. So if you wanted to know what the solution curve looks like, if you wanted to sketch the solution curve, you could from this, which is nice. Not that you couldn't from the other way of writing it, but most of us would be more likely to recognize this as a circle from that form. Modulo my bad art, this is a circle. Which is nice. If you want an explicit solution, you can get one too. By solving this for y, I get y equals 1 of plus or minus the square root of 2c minus x squared. And you might recognize that as a circle, you might not. What we were dealing with here was an initial value problem. So if we want to solve the IVP, we still need to plug in our initial conditions, right? This circle, this expression, is the general solution to the differential equation. But when we throw in these initial conditions, things change a little bit. So let me go ahead and plug in those initial conditions and see what we get. I like this form, so I'll go ahead and plug the initial conditions in. Really what choosing those initial conditions is going to do is it's going to specify the radius of the circle. So this says when x is equal to 4, y should be equal to -3. So -3 squared, that's the y, plus 4 squared is equal to 2c. I'm plugging those, I'll label this. This is equation 1. Plugging the initial conditions into equation 1. Um, 3 squared is 9. 4 squared is 16. So 9 plus 16 is equal to 2c. 9 plus 16 is 25. So 25 is equal to 2c, which means c has to be 25 halves. And then you could take that and either plug it in here for an implicit solution to your IVP. Y squared plus x squared equals 25. Or y equals plus or minus the square root of 25 minus x squared. Solves the initial value problem. So your final solutions here. This is good. Final answer here would be this if an implicit expression is okay, or this if an explicit expression is required. If you were additionally requiring that your solution be a function, right? Neither of these are functions because the graph fails the vertical line test. You could just take the plus or just take the minus. Okay. Questions about this example here? Questions about separation of variables in general? Alrighty then, well, you guys now know the most important method for solving differential equations. You'll see when we talk about modeling, you have seen if you've taken physics that differential equations are the language that the physical universe is written in. It's much easier to describe the forces and hence the accelerations of objects in the real world. I can't say exactly what the path of a particle under certain influences is going to be, but I can pretty easily write down an equation describing the forces that that particle is subject to. So solving differential equations is by far the most important skill for an engineer or physicist mathematically. And these are the type of differential equations that show up most often in those settings. One last thing before I let you go. I'm going to show you a tool that we're going to use next week. So this is GeoGebra. If you've heard of GeoGebra before, that's awesome. This is a little applet within GeoGebra designed to draw slope fields. So I was playing with this earlier. This is the best thing I found like that. I want to show you what we get if I input the differential equation we were playing with. Oh, let me turn this off. So here's the equation we were just messing with. And if you take that differential equation and you plug in points from the plane, you know that dy dx, that's the slope of the function y. If I come in here and I plug in the point 1, 0, or 2, 0, I would get like 1 over 0 or 2 over 0, which we would interpret as infinity. So I'd say that slope there is infinity. If I plug in the point 1, 1, then I would get negative 1 over 1. So you see this guy right here has slope -1. We draw all these tiny little line segments with the slopes given to us by our differential equation, and that will tell us kind of what the solution curve is going to look like. Depending on where you choose to plop your initial conditions, oh, this is doing something funny. I haven't looked at this one yet. Depending on where you choose to plop your initial conditions, you can get an idea for what your solution curve will look like. Now, the numerical tools for this are throwing some weird shit out. But in general, you can play around with these things and have quite a bit of fun. I experimented with some simpler ones earlier. And I think playing with this will help you understand that existence and uniqueness theorem a little bit better. As long as this function is continuous and has a continuous first partial derivative with respect to y, then you will be guaranteed the existence of a unique solution. And specifically, as long as that function is continuous around the point you're choosing for your initial conditions. So x plus y is continuous everywhere around the point I'm choosing for my initial conditions. And so no matter where I drop this point, I'll get a solution. And again, you see that kind of behavior we talked about with the e to the x equation, the very first one we looked at, where all of the solutions kind of share an asymptote. And that's going to be important when we talk about something called stability. So next week, that's what we're going to be doing. We're going to talk about direction fields. I'm going to show you how to solve all first order linear equations, whether they're separable or not. And that's an exciting thing also. Those will be the two main topics for next week. There'll be a few other little things. We're talking about models and other stuff, but that's where we're at for today. And that actually means we've gotten through all the content that I placed into your homework that's due next Monday. So tomorrow on Thursday, I'm going to go ahead and deliver the direction fields lecture, and we'll see kind of where we are. We'll take some homework questions if you guys like. Any questions for me before we depart for the day?
I had a question. Since we are still on track for the exam next week, do you know when exactly we're going to get our study guide for it?
So I will release the study guide on WebAssign here. I have to think about exactly which day I want to do the test. So I don't have an answer for that right now, but I'll have an answer for that tomorrow.
Okay, thank you.
Sure. Any other questions before we go? Alrighty then, guys, I hope you have a lovely rest of your day. Office hours today is from 3 to 4 p.m. Come by if you would like to talk about anything. Otherwise, I will see you tomorrow.
Have a good day, Professor.
You too, Ernesto.